There's a difference in databases between the data that you store in a table itself, the table storage, and the data that you store in an index. And there's, for one, just kind of some good stuff to establish about how this works, and then also some trade-offs about how you have indexes point into the place where the table data is actually stored. We have some example table data. So this is a sample users table that, most applications need something like this, whether it's in Postgres or MySQL. And then this is not a sort of really realistic looking B-tree index, but something along the lines, right? A tree-like index. We're just going to be vague about it. If you want to learn more about B-tree indexes, I've actually written blogs on it, a blog on it, but there's lots of other information out there. But essentially, right, when you have a relational database, you store the rows of a table in some file somewhere. And there's different ways of organizing this. Here, I am just showing it as a simple box with a bunch of rows in it. If you are MySQL, the way that this data is stored is actually in a B tree, which is a special kind of tree that is really well optimized for database type applications, essentially a tree that works well with the semantics of how reads and writes happen on a hard drive. And then in Postgres, it works a little bit differently, where all of the rows are stored basically in just one big tuple file, and it keeps track of which space in that file is available for new tuples or rows to go into. It can also append new tuples to the end of the file. So the exact way it's laid out on disk varies from database to database, but you generally have some file where all of this stuff is well organized. But then indexes are what we use to make a lot of different queries and lookups faster. And indexes, again, are often built with these B-tree structures, but sometimes they're built with hash-based structures. Sometimes there's even specialized like geospatial ones that use R trees or graph-based indexes. But here I'm just showing, like, our example is this is a simple index. The interesting thing is, right, like you have a single table, and in MySQL, actually, by default, it builds the table data into a tree that is indexed based on the primary key. So if we say the ID here, it would actually already be indexed on that. So lookups based on ID would already be fast. But if your application needed to do lookups by username, right? If you wanted to say, select all the rows from this table where the username equals Jim, if you don't have an index, it will have to scan through all of the, well, in this case 4, but maybe millions or billions of rows to find all the Jims. Whereas if you have an index, whether that's hash-based or tree-based, it can narrow down the result sets much faster, and therefore that query will run a lot faster on the database. So we often build on a single table, sometimes a single index, but sometimes a single table can have 2 or 3 or 5 or 10 different indexes all on the table on different columns, or you can even have a single index that combines multiple columns into a single index. Because if you know, like, hey, often people are looking up both by like username, but maybe people can have duplicate usernames. So we also want to include email in the index. You can have those in a composite index together. So in this case, I'm only showing one, but there might be 10 extra indexes with other column information in it. And so one of the things to be careful about is if you have an index, one index or 10 indexes, every time you insert something new into here, so I'll extend this out, and let's say a new user just signed up for my app. So we have user 5 named Sam at hey.com. He lives somewhere, and whatever, I guess we have to pick today, right? 12/29/2025. So new user just signed up. If you did not have any other indexes, all you would have to do is write this, right? Once that is written to the table, now everything is up to date. If I have one index, I also have to do this additional write to make sure that Sam is now in the index, so that future lookups for, users based on their username will go fast. So I have to basically do multiple writes. This is a concept sometimes called write amplification, if you read about it in database books and stuff. So my writes are amplified where I actually have to basically do 2 things every time I do an insertion. And you could imagine if I have a table that's queried a lot and I have 10 different indexes on it, every time I insert one row, I might have to also update 10 other places in my index. And this is a place where the whole idea of logging, like write-ahead logs and stuff, help, because you can't actually write the new data to a log and then only do the index and table updates in memory initially, and then later on you can flush those things to disk. So there's like ways to optimize this and make it a little bit more bearable, but ultimately it amplifies your writes, right? And it makes every insertion slower. So this is why indexes are great, but the more indexes you have, they take up more space on disk. So you're essentially, it's a time-space trade-off. This is like the ultimate computer science trade-off that if you've ever studied CS, it's like what's constantly talked about in algorithms is you can often make things faster time-wise if you utilize more space. And if you want to utilize less space in RAM or on disk, you often have to do things more slowly. It's this like perpetual trade-off. You can use more space on disk, but it saves you time in queries. But then there's also this problem of the write amplification, right? So this is the balance, and what, a lot of not just designing the databases themselves, but if you are like a DBA or someone who's a performance specialist, right? You might come in to your company or to other companies you're consulting with, and if you're trying to improve their database, you would probably look at what are your tables, what are your indexes, what are the patterns of queries that are running, what are indexes we should add to make queries faster, what are some that we maybe should remove because they're wasting a bunch of disk space, but we don't really use them very often for queries. So there's almost like a whole industry here, but a whole sub area of tech of just like, how do you optimize indexes on a database? And then the other aspect though that this book talks about as like kind of an interesting trade-off is if I have this index, the idea is, and again, this is not a precise B tree, this is kind of a loose B tree, but if I have this and I'm doing a lookup for user with name Sam, I would come into the root of the tree and then I would go down the route to Sam and I would find, hey, Sam is a username in my database, but now I need to go find the row that corresponds with Sam. So somehow I have to get from my index, which is in a different place on disk right here, back up to here so that I can fetch all of Sam's data, right? His username, date he signed up, all that. So how do I do this? How do I make the link or the reference between the index and the table data? And two different ways are contrasted here. So one is, and we're gonna kind of oversimplify it a little bit, but let's I'll zoom out slightly. So one thing we could do is we could save an actual, essentially direct pointer to like the page on disk where this lives, right? I'll just make up a page address. So if we actually stored like, here is exactly where on disk the SAM entry is, once we do this disk lookup, the very next IO operation I can do can be accessing the SAM row and getting that out. Really good for performance there, right? The trade-off is we now have introduced potentially a lot more index maintenance that we have to worry about, because if I ever, let's say I have to update this, and some databases like Postgres, if you update this row, they actually rewrite the row in a whole new location on disk. So now I have to update all of these in every index to the new physical place on disk where it lives, right? So basically the advantage is that performance at index lookup time, but there's this trade-off of now I've introduced all this maintenance for any time that moves to a different spot. Now I have to like change this link, right? The other thing that I could do is whatever the primary key of this table is, like I was talking about in like MySQL, all of this data for a table is actually stored on disk in a B tree that has the key with ID. Right? So you can do quick lookups to any row in a B tree based on the ID. So if instead here I stored 5, 4 for Jim, the nice thing about this is generally your primary key for a user, the user ID, probably doesn't change very often, if ever, right? It might never change. So once I've found Sam, I know Sam's user ID is 5. So I have to go do another lookup into the index that's up here, which might require a few IOs, or maybe even just one if some of the B tree is already in memory. So it might make the lookup, the query itself, when I'm trying to look up Sam's information a little bit slower. But the advantage is now if Sam, I have to rewrite this over in the table and put Sam in a new page on disk, the ID is still 5 for Sam. So this lookup in the future, as long as this index is properly maintained, I don't have to go update the other indexes just to make this work. Now, I've oversimplified a little bit because in Postgres, you can have multiple row versions, and sometimes you still have to go update these things, right? There's always, more to the story than you can cover in a short YouTube video or live stream. But that is, one of these trade-offs, right? In the indexes that are pointing back to the main data source itself, there's pros and cons by choosing like direct ways to get to the data versus indirect ways like identifiers. And this is one of the never-ending perpetual trade-offs of designing a database system.